Good afternoon to everybody. So the topic is validation of smart physical systems. I was guest at Professor Horváth, so this is also part of the common results. In the beginning, I will introduce what is a challenge at validation, especially at smart system. It is a tough work, therefore I will start with presenting how is done validation at traditional system. Then I'm going to present a proposal, it's a working version, how smart system should be validated. Maybe to repeat the word validation, it was introduced already in the morning. So when this traditional V system, we specify the system, then we go from more general, we check at customers, and then we go to subsystems, to parts, and then verification is when we check the specification, if it's according to specification, and validation is more on high level, if from the end user point of view, from the function of the system, are requests fulfilled, then it's validation. It's the purpose of validation. And what's the problem at smart system? So here we have a traditional system where we do product or system development, and then we validate it. And the system operates in the way as it was designed through the exploitation phase. So we call it that we do it in deterministic way, but at smart system, I will present definition of Professor Horváth later. The problem is because the specific of smart system is that it adopts the characteristic, it evolved through the exploitation phase. That means the system is after 2 years of operation different as it was at the end of development phase. Therefore, it's a tough job to validate system that is going to develop further. That means we need to build in self-control, self-validation features that enable this self-adaptation of the system in later phases. So to check, to present how it's done in the classical system, part-time I work in a company where we produce medical devices, and according to the regulatory requests, validation need to be done, and even for this system it's a tough job. So the company need to have validation master plan. It's like guidelines, a concept how they guide engineer to do this validation process in a proper way. We start then with product specification, and the first step is risk assessment. So we simply cannot, especially with more complex system, we cannot focus to all details. Therefore, we need to assess what is critical, and then through the validation process, we focus to these topics. So we prepare then validation plan, execute validation. Typical phases are installation, operational, performance validation, and it's important to record well all the validation steps, because this is later as a proof that the product works according to specification. So if everything goes fine, then we prepare a final report. In some cases, we need to do some corrective actions, or we need to improve at least some modules. So I would like to repeat once again that validation process is a tough job. It's time consuming. We need to have highly specialized personnel, and we should be aware that it's costly. In some cases, like for airplanes, the control system validation is half of the development costs. So how we perform risk assessment in the company is the failure modes and defect analysis. Because the company has background in automotive industry, this is a known method, and we apply also this method for risks. We can use some standards. They are guiding us what are potential risks, and it's like a checklist, what should we think about. And then we assess each risk, how critical it is, and we decide, does it need validation or not? For example, in this case, we are checking traceability in an information system. According to risk assessment, then we prepare validation plan. In this case, we prepare it detail in what way the system will be checked. In this case, we are checking if we change a document or system configuration, do we have records in the system, and we define who will perform this and what are criteria that the validation of this step is accepted or not. And before we go further on, once again the definition of the smart system according to Professor Horváth definition. So the cyber-physical system can be split into several generations, and the second generation has the capability for self-awareness and self-adaptation. Then the third generation can self-evolve itself, and so from the second generation on, we have the so-called smart system. An example is, for example, a self-learning robot. It is evolving, adapting the algorithm through reinforcement learning. That means after 1 year of operation in specific environment, this robot operates in a different, more optimal way as it was at the beginning of when it was just finished and start to work. Maybe a simple comparison to explain it again. So a baby is like a traditional system. We should be very careful how it operates, that all conditions around are fulfilled. So a child is like quasi-smart system. It can conduct several tasks well, go to the local shop and buy ice cream, so we don't need to give all instructions. But engineers are, as an example for a really smart system, they have all the freedom, but important is they have this self-control. They design the systems in a way that they are safe and reliable. So it's the feature of smart systems. Maybe it sounds that it's like a science fiction, but I would like to stress when I was comparing these different materials that for complex system, we very often discuss about the complex system, several solutions, principles that are applicable for smart systems can be very helpful for complex system. Like at hardware we have redundancy, dissimilarity, then runtime monitoring, fault tolerant techniques. These all approaches can be very useful, and also for smart systems we will see that they are necessary. And here is a proposal for the validation of smart system. Here is a comparison with the traditional one. The backbone of this proposal is taken from traditional one, and then we have some additional activities. In a minute, I will explain about the validation of system design, about the checking of building blocks, and execution of validation plan is also need to be different because we cannot do step-by-step validation, but it should be done in automatic way. How to perform this validation of system design? As a template, as the base, was taken the rules for fault-tolerant aircraft design that is used at aircraft. So I'm not going through all the details, but we have extended this list with some details. So already when we are checking design, we should be sure that the system has implemented self-constraining rules, because we have say the system is evolving and it has to control itself how it is evolving, and this need to be checked. The system has to have capability how to react in safety critical situation. It need to have self-awareness capability, and it need to adapt to new circumstances. So risk assessment, we have already a few details about the traditional systems. Everything need to be repeated also for smart systems, but some other topics should be considered. There are not all of them, especially what has to do with self-control, safety. We have already said these self-constraining mechanisms. This additional topic need to be considered. What if this self-constraining mechanism does not work, and we need to, during the validation process, we need to check these additional features that need to be implemented. Also in the morning, very often was stressed complexity. There is the one conclusion that when the complexity is growing, we should fight with it with the smartness, with autonomous blocks. So in the decades ago, we need to, when we were using sensor, we need to specify all the parameters. Nowadays, the sensors should have data how to set parameters. It need to tell the system that something is wrong if something go wrong. So with this approach, we need to be careful when we are building a system from blocks that we reduce complexity. As we have example with a child, we just say, go and bring an ice cream. We don't need to worry about all details. And similar approach needs to be done also at complex system. The smart subsystem needs to check for themselves. So we have some other focus. Can the system detect the faults in real time and react? So the system should be independent from the additional control. We need to classify the components subsystem according to priority, and that we need to focus to the right one. And if we can do something on the subsystem level, on component level, we should do this validation separately, that we reduce the complexity of the whole validation system. Few things about the execution of validation. again, we will not go through all the details, but we need to plan and execute if this self-constraining mechanism works. So, do we have a perfect system? I'm saying that recently we were read in newspaper that a driver in Tesla car was killed. And everybody is worrying about these automated driving cars. But are we aware that over 25,000 people in Europe only die on streets each year? And Las Palmas have about this number of people, but this is the number of people that are seriously injured. So I believe that smart system can be more reliable than human are. So I am not going to repeat. Several of details was already presented. What's the differences between traditional, complex, and smart CPS? Maybe a few words for the conclusion. So this, I believe that validation is part of smart system. It should be considered during the whole development, all the development phases. And I don't see this as big boom. It is step-by-step approach. The smart system should we should prove that they are reliable, and also, as it was said, on complex system we can already test several approaches, and then we will many things need to happen in minds. We need to think differently, because the current legislation does not allow to use a smart system in safety critical operation, because they don't work in deterministic way. And as it was said, so we are not bringing solution, we are more opening question. So many things need to be done before the smart system will be more spread as they are nowadays. And so I'm opening discussion. Professor Horváth will add something.
Actually, I will step in as a chairman at this very moment, and I will kindly ask one to set up the presentation. In the meantime, when I'm taking the questions, please, do you have remarks here? Do you have questions for that presentation?
Yes. So, very good talk, on the systems itself. If you can go back to the slides where you compared the traditional versus, the three columns, right? So you're talking about systems at the systems level, right? But systems are composed of components, right? How do you validate the information exchange? Have you addressed that? Because I felt that traditional models, the validation approaches of this flawed, cannot be applied because you can't compare a cyber-physical system, right? The next generation cyber-physical system to just another technical system. I feel that's a flawed assumption. Sorry, I'm putting you on the spot, but let's see how you answer. That's number one. Second is information and data exchange. The accident that happened there, you can't justify it by saying, well, this happens with humans and we do less than that. If it was a technology-based reason, which could be latency, inability to respond very quickly to uncertain data, which it looks like offline with some of my friends' work, that was the reason. It could have been a data exchange problem rather than a logical problem, because most cameras, can track a person, right? So I don't see that in your list of validation principles, because if it's not there, then more accidents are going to happen, because the crux of this is the systems by themselves will work together. It's the integration of these systems and the rapid response to changing data, which probably most systems can't avoid unless they are really very agile and super fast. So it's a challenge question. I don't have an answer. I want to see whether you looked at it.
Would it be so nice to take the question and formulate an answer?
Or we can talk offline. It's a long question.
Your right is to answer the question.
You argue that we cannot compare traditional and smart system. So several approaches are, for example, according to definition, the system that controls airplane, it is not smart. It's developed and it's validated and it works in this way. But there is the weather conditions are different. So I'm saying that even the traditional system have quite high level of uncertainty, and it's not so straight border between traditional and smart. So there is a difference because they are evolving, but this uncertainty is even in traditional system already there, and we many approaches that are making the system more reliable.
Right.
They are useful for both cases. And smart systems are adapt to new circumstances better. So we are saying that they have potential to improve in comparison to the traditional systems, because this hierarchy, it works to a certain limit. If we, for example, check the processes in our body, they are not centralized. Like immune system,
right.
it's already smart system. It's developed, and maybe we should change our way of thinking from this traditional to
something more organic.
Yes, that is work autonomously in small, like for example, the small animals, they work independently,
right?
But they work as a system. They are efficient.
Yeah. So my point was, it's not that it won't be sufficient, but it would be nice to have a 7th or 8th bullet, because when you talk about today's cyber-physical systems, the emphasis has got to be on information as well. Information systems behave radically different from non-information intensive systems. And I don't see that there. That's what I was trying to say. If I was doing it, I'll have a 7th point that talks about the reliability of the data exchange and how you address that, because they've evolved, right? It's an ongoing evolution, and that criteria needs to be there. If that is not front and center, any validation, I'm making an argument, because we started a panel meeting a few weeks ago, the systems of validation is going to fail if we don't address the complexities of the data exchange itself that can cause the entire system to fail. I don't see that in any of the umbrella. That's why it is just a suggestion that it needs to be looked at. If you can't compare, a smart system from the 80s, unless I missed it. It could be, now you have the communication.
So the communication is
all right.
Definitely an important, also how responsive is the whole system. It's not just the logic, because it's a time frame.
Point taken. So it's just that I'd like to see that, if I were you, in the next chart, because that changes things, the communication of the components, right? That's a good area to look at, which may not have been looked by.
Yes, definitely, but
it's there.
It's more general view.
I apologize, the chairman has given more.
Sorry.
Next talk about communication.
Clarify something for the takeaway point of view.
Very good.
The things I wanted to say was major differences, not much the determinism principle is true for the system.
The system.
Because if the system throughout his life remains what it has been designed for,
Right.
it causes completely different problems or different issues from the point of view of validation than a system who is continuously changing during his operational lifetime. And this is the main problem, what I feel here, and I believe needs more attention, namely that what can we do with those other systems which are continuously learning, adapt, evolve themselves over the life cycle, and then what can we do with these systems? But obviously here I am not to raise questions and give answers. I am just a chairman, and therefore I have to thank the presentation.